Hello participants, and hello guests and members of this webinar. I'm delighted that you can join us today. Before we move on any further, I need to inform you that this is a recorded event and it will be being recorded today for use elsewhere by ATSE, and you should be able to see the recording icon in the top left of your screen. However, before we move on to hear from our two very renowned speakers on this exciting topic of autonomy and automation in the mining industry and in other industries I think we're going to see, I would firstly like to acknowledge the traditional owners, the traditional custodians of the land on which we meet today. These are the Turrbal and Jagera nations, and they are the traditional owners and custodians of the land in which we are meeting tonight. I pay respects to their elders past and present, and to any Aboriginal and Torres Strait Islander people who join us here today as we share and discuss our own knowledge and practices. We also acknowledge the deep knowledge forever embedded in their custodianship of this country. So this afternoon, we're going to hear from Ross and Sue, and you're going to listen to the world of autonomy through their eyes, and they are very renowned speakers. What we intend to cover and how this will flow will be two periods of presentations, firstly from Professor Ross McAree, and secondly from Dr. Sue Keay. I'm not going to go through the full introductions. You want to hear from them and not from me. Their biographies are on the material that has been sent out to start this webinar. As we go through, what I would like to encourage you to do is to put on questions and answers using the tab at the bottom of your screen. So I will be monitoring those questions and answers, and I will be pulling those questions and answers together throughout the event. So I'd like to hand over now to Ross, who's going to talk to us with his presentation title of Autonomous Systems. It is a trust thing. And Ross will run for about 30 minutes, and we'll have a question and answer facilitated session that we can cover off the matters that Ross brings to the fore. So Ross, I'd like to hand over to you.
We're up. So thanks, John, for hosting the event today, and thank you also to Sue for making yourself available to talk. I'm going to give a perspective, I guess, a bit of a meta view of some experience based up by a case study. My main points are really that autonomous systems are possible. They're technically feasible, but they will not deliver their full and potentially very significant value until they are trusted. To enable autonomous systems to be trusted is an interesting challenge that I think requires some redress of the way in which we engineer them in order to take into account the socio-technical and socio-economic factors that are at the core of what might be called trust issues. And I'm going to illustrate these points by a case study, but that case study could be one of many. We think about the dictionary definition of trust. I think it speaks to something very visceral, that if we don't trust, then we, as people, will treat with suspicion anything that fails to meet our basic test of trust. And more than that, we know ourselves that we need to be able to win trust from others, and so it is with autonomy. There are, I think, broadly 6 technical dimensions of autonomy. People working in the space of robotics and automation will generally have a specialization in one of these areas or spread themselves across all of them. They're all relevant. You know, at the bottom of the problem core is a control problem, and in any control problem, we need to sense, we need to decide and act. So there's questions of how do we sense, and from that, how do we create perceptions, and in turn, how do we build an awareness of the the system around how do we plan missions against that awareness, and of course humans are always going to be part of these technologies at some level. So how do we engineer for the man-machine interface? And I'm not in any way suggesting these are solved problems, but I think there's enough technical evidence to suggest they can be solved. There are those other dimensions, in order for an automation system to achieve, I guess its goals, it has to be safe, first and foremost. It has to actually work and achieve value by doing so. It can't bring unacceptable or unintended consequences. There will always be some unintended consequences, but we need to make sure that they don't cross the line between what might be accepted. It's going to make our workplaces and environments better. It's not ever going to, any technology that makes work harder or less effective is never going to win out in the long run. It's got to support sustainability, so bring about reductions in energy consumption or achieve better yield of whatever the operation is. And I think it should not give rise to a robotic apocalypse. We don't want to create a world in which we are run by the robots, so to speak, even if that's maybe a bit of a stretch. And of course, there are other things there, but these are some of the core dimensions. And if these things are achieved, I'd say the technology is trusted, and that's important, because the corollary is it's not trusted. If we don't manage to meet these and the other dimensions of trust, which are inherent in an effective technology, then we've got a fundamental problem. I'm going to give you a case study, and the case study is one I've worked on with an equipment manufacturer for 10 years. And it's one of a number of projects that my group has been done. These are autonomous bulldozers. They're without drivers. They're working to, in a coal mine, performing effectively a strip mining operation. At this point in the operation, they're filled in the void and they're starting to backstack material still above coal to bring it up to uncover that coal. And these machines are pretty effective. You'll see they've got really good blade loads. There's a little bit of track slip occurring, you'll see there, but they're pushing at a rate which is comparable to a human operator. And indeed, on a push-by-push basis, they're more effective than a human operator. And there's every reason we should, I think, on face value, trust this technology. Just to give you a little sense of what's involved in it. The system allows a single operator to supervise a number of machines who operate autonomously. They complete packages of work which are typically 15 to 20 minutes long. These bulldozers work in slots, and they will typically progress that slot by an amount consistent with that amount of work. There's algorithms that keep track of the workspace in which the machine's working, and they plan based on the internal model of, if you like, the geometry of the terrain. The sequence of operations that will bring the machine or bring the process to conclusion in the most effective way, whether that's measured by fuel burn or time or some other measure. An operator sits at a control station. You can see the control station in this video, and can take control of a bulldozer, effectively teleoperate it when that's needed. And that's needed when the dozer gets stuck or where the bulldozer needs to move between slots. Operators can override the missions that the system generates and otherwise shape the behaviours of the system. And in engineering this system, all of these considerations were part of it. The particular part that we've looked at UQ has been the mission planning component of this. The idea that we might be able to choreograph a fleet of bulldozers and associated machinery. There's a need for excavators to make space for the dozers to continue their work, and come up with a very efficient means of moving the dirt that needs to be moved to the location that's been designated for its final place. And it's been a significant focus of a number of projects that we worked on, I guess, over the last 5 years. Our inspiration, in a sense, for some of this comes from a quote here by Bruno Walter, who's a German composer, a piano player, and very talented. And his sort of observation around the playing of piano is that by concentrating on precision, one arrives at technique, but by concentrating on technique, you don't necessarily get precision. And this has been part of our thinking around a whole range of problems. I'm not going to go into those now, but I'm going to sort of illustrate the idea by a little video. And what we have here is a terrain as it existed at a certain point in the process. And what's happening is we're using some algorithms. They might be classified as artificial intelligence algorithms to plan out the motions of a fleet of bulldozers. There's 4 bulldozers in this case. You'll also see that there's from time to time, some movement of material in front of those bulldozers. That's a simulation of an excavator that's giving the bulldozers space to move right up against the back wall or high wall of the strip. I'll just play that again. Various things happening here. The behaviour is being simulated so that constraints are met, so the height between slots is never exceeded a defined amount, which would expose a risk of tip over. There was a tip head that you could have seen was advanced as best it could equally across the face to fill in the void, and then there's this backstacking of material at the end. And through various processes, the system has established that, subject to constraints, this is the most efficient way to move this dirt. And the concept underlying this is that we continually replan this process. Process depends on the state of terrain at any time. And when a bulldozer chooses to act on the terrain, it will move it, but not entirely in the way we predict. And so we constantly replan and take the first action from that, and then replan, and so it goes. And this is sort of choreography or sequencing of the actions of the individual machines, the dozers and the high wall excavator. Now, I'm going to talk about what actually happens now. How do these autonomous bulldozers spend their time, and why trust is important here? And this was a study. Don't worry about the categories here. I'll speak to them. But the idea is to take the total calendar hours that the machines were available. I think in this study there were two machines in operation, and for the period of the study, about 151 hours of operation. Of that, the amount of time that the bulldozers spent either performing autonomous work or being teleoperated was around about half of the available time. So around about 50% utilisation, so classified as broadly machines are working and not working. And there are a number of reasons why they don't work. There's issues around autonomy itself. There's issues around the machine, and in particular communications issues tend to crop up and cause loss. There's this group we call commanded idle, which includes a large category of what we call teleoperation, termination, remote, and then autonomous pending. And if I look at the large categories here and ask, well, what's going on? I find the first of them, which is labelled as unknown, but really means that the system is waiting for permissions to do its work. There's a complex chain of interlocks which must be met in order for the machine to work, and if one of these conditions is not met, then everything comes to a stop. This is a loss of about 4 hours out of the 70. So not a huge loss, but still an important loss. And it's characterised by the fact that the engineering of the system to meet the requirements of functional safety has undergone a process which locks it into conditions where it's unable to progress because the permissives are not able to be established. And there are a number of reasons for that. But I think the core, maybe there's some engineering that's gone on here, which has not necessarily allowed the system to achieve its desired function of operating, because it's locked in this sort of difficulty or the complexity of the systems problem. Here's another group of quite large ones. These are categorised as tele-remote termination normal, but in PRACE, in this case, the system's been stopped by the operator. In particular, the operator stopped the machine because he's wanted to take a crib break, either a toilet break or a lunch break. Now, the system could be capable of working on its own through those times, but under the regulatory requirements under which this system has been implemented, someone needs to sit in the seat and be there to watch over it to make sure it doesn't go wrong again. It's a trust thing. In this case, this other category is 10 hours available to be put into autonomous mode or model, but needs operator input to do so. Again, the operator may be preoccupied with teleoperating a machine to move a particularly large rock. It might take some time. In that time, the missions might expire. Yet those missions are there and ready to be planned, and they could be actioned if we trusted the technology sufficiently to do that. So we see the larger categories here. All of them have their core, what you might think of as trust issues, that we don't quite trust the technology enough to allow it to do its thing. So how productive are they? Now, this is an interesting point. I've got 3 graphs. This is calendar time on the base axis, and on the y-axis is material that's moved to a location where it won't need to be moved again. So it can be considered a final location for that material. And it's measured by cubic meters. And so in calendar time, this is the progression of material, if you like, into that primary location where it doesn't need to be moved. If I take away my losses, I'd end up here on this green line. That's quite respectable productivity. It's slightly better than a human can do if measured under the same terms, but it's not as good as this red line, which is our predicted model from that theoretical simulation of the productivity that could be achieved. And so these are our utilisation losses, the time that we're not actually operating. These are our precision losses, the losses that occur because the actions that the dozer takes are not as precise as they could be. And this is a little bit perplexing because we're planning out those missions fairly closely. So I'm going to show you a play for this data which says what should have happened and what actually happens. I might stop this one. And here's the planned sequence of motions for or pushes for the dozer. You'll see the tip head's progressing. It gets to the point where we hit the low wall, and then we start backstacking material upwards to achieve a final grade where we've taken the material down. And this is what is actually happening with the technology. And you'll see there's some differences. The first difference that you might notice is the system is not tip heading. It's actually pushing material downhill and backstacking that material downhill if you watch it. There's some more dozers here because because there was some manned operation happening alongside. But you see, there's a sort of process rather than tip-etting and letting gravity do the work and material falling over. The operator's coercing the system into a different behaviour. He can do that, and that different behaviour is to backstack downhill. He then gets to a point in the process where he decides that he might do a little bit of teleoperation work. Well, no, he's going back here. He's going to play around with material and move it quite against a plan that has been simulated. And he's had to do that because there is a lack of a high wall excavator available to do the work. But you can see quite fundamentally different operation. The operator's forcing the system to behave differently to the way it wants to. He's got the power to do that, but it results in a number of efficiency losses. When investigated as to why this was done, the argument was that the process that the operator looked to implement was the one he'd been himself trained to implement many years ago, which wasn't necessarily the most efficient way to do the work. And so again, we hit this issue of trust. He doesn't trust what the technology is suggesting is the most effective way to do the work, but instead looking to make it work in the way he wishes to make it. And there's a loss. Okay. Now, this case study has a pattern that I've seen a number of times in projects. I've worked on it. It's collaborations typically with manufacturers and mining companies. You know, I think the engineering process across the group is strong. The problem's appropriately understood and described. Good methods are used to underpin the engineering effort. The technology meets or exceeds its functional requirements in testing, yet in implementation, it struggles to deliver even half of the prospective value on the table. In this case, the system was arguably delivering around about a third of the value that could be there if it was to really operate as smoothly and as effectively as it could. And in this, trust issues seem to be the limiting factor that comes into play. Now, I'm of the view that we arrive at this situation because of our focus in engineering effort on the purely technical. And we need to rethink complex system engineering in order to overcome some of the boundaries which are present. So we have some really good methods for the purely technical aspects, and I think the technologies have matured significantly, both from a research point of view and a commercial point of view. But there aren't effective methods within this space, or more broadly within engineering, for understanding these socio-technical and socio-economic considerations. They don't factor into the final design, and because of that, we're unable, I think, to buy the trust of operators. They feel that the system is not able to give them confidence to let it do what it needs to do. Now, there's been some really good academic activity in this area for maybe the last decade, and I point out the Systems Engineering Division at MIT as a good example. Nancy Leveson has done some fantastic work on looking at safety aspects and how we build more effective engineering solutions by using system theoretic concepts to study safety. But regardless of this, they're not in common use. And to be honest, the culture of practice rejects them. There'll be people who like to bring the problem back to being a purely technical problem and reject the need to take broader considerations and do the upfront thinking that might result in what I think is necessary change. There's lots of compelling challenges here, but it seems to me one of the most important is, how could we educate our graduates so that they had a focus or an understanding and fundamental strategy of trying to build trust into their systems that they're involved in engineering. And this is something that I do think needs address. So with apologies to Bruno Walter, I might suggest that by concentrating on trust, we can arrive at effective automation technologies. There's some work there to do, but I'm fairly certain, having lived the experience many times, by concentrating on the technical problems of automation, we don't achieve trusted autonomy. So at that point, I'll hand back over to John, and I think you were going to look at questions, John.
Thank you very much, Ross. That was really interesting, and it brought up quite a few memories for me being involved in this area quite a long time ago. So we have two questions coming in, and the first one is from Ian Cameron, and he says that assuming that trust has to be earned, how much of that trust can be generated by autonomous, adaptive trust building processes, essentially independent of human input? So taking the human out of that loop as I read it. I'd be interested if you've got any views on that and what your reaction is, Ross.
It's an issue. It's a good question, Ian. I think I'll make this point. Context is, in the work I've done, context is fundamentally important because it does shape the way in which you conceive solutions. The area we work in terms of, I guess, what you might call the AI side of this is to arrive at rational decisions in a bounded amount of time. And in order to do that, we need to provide constraints that allow us to effectively search a space that's there. Could it be done automatically? Oh, I think in time, but my own view at the moment is that there's still that human dimension that makes the problem solution tractable in terms of defining what we call strategies and methods that keep the solution going in the right direction and in a way which is near to optimal when solved. So I don't know whether that answers the question, Ian. It's a good one.
Very good. So if it doesn't answer your question, Ian, feel free to raise another one that we'll cover at the end. So I hope that's useful. I'd like to get on to a question here from Mike Hood. And he says that his observation is that the issue might be that the operator doesn't trust the technology, which is as you suggest, or alternatively, it could be that the operator feels redundant and feels bored sitting still for a whole shift, watching the machines do their thing. This is kind of the human-centric matter that you put up earlier on. I'd be interested in your views.
Absolutely, Mike. And I think we're all good at rationalizing. So in this particular case, I illustrated that the operator chose to make decisions that were different to those which were being planned for by the system. And the way they rationalize their behavior is they don't trust the technology. So yes, I think they're bored. They're bored. They're sitting in the seat because their technology isn't trusted in the first place. And the way in which we meet the overall need for functionally safe solution is we say we're going to have a procedural control that sits above all other controls. And if this thing goes out of control, then the operator is there and he's going to take command. But they don't need to be there. And they are bored. And they meddle. And they meddle and rationalise that on grounds that they know better. They have better judgment. And this is at its core, I'm looking for a label in trust that captures the many dimensions of this, but this is part of it.
Well, thank you very much, Ross. That was very good and very insightful. What I'd like to do now is move on to a question from Alice Clark, and this is very topical. She firstly says, "Great talk, Ross," and I think we all agree. But she asks, "Do you have any comments to make regarding trust and the spectre of cybersecurity in these systems?" Look, I've got a smile out of you there.
Yeah.
Over to you.
No, look, I mean, this is another dimension of it, and you know, they're all birds of a feather. These aspects, but yeah, the cybersecurity is an important and growing concern. And we've had at least one experience where there's been an attempt to break into the system, and I'm sure there are many examples of that.
Okay, we have a excuse me. Quite correct. That's a very topical matter at this moment in time. I've got a question here from Rowan Gilmore, and it's an interesting question. He said, "How can trust be earned when technology may not have the right answer? For example, how does an autonomous car know to stop at a pedestrian crossing if there's a person waiting to cross or just standing there?"
Yeah, good question, Rowan. How does a human driver respond in those circumstances? And I think the answer is they look for intent. They either look for actions, or it might be as subtle as eye contact, or it may be a movement. These technologies have to develop the same capability, and there's no question around that.
Thank you. I've got a question here to Julie, from Julie Beebe, to you, Ross. And it's an interesting one. It's one that we specifically face in the mining industry, which is a high level of trust is required for automated and manual equipment to operate in the same area. How successful have such trials been so far? So that's automated and manual equipment, or autonomous and manual equipment working within the same zones.
Good. So the example I gave you, Julie, was of a manned excavator working with unmanned dozers. And I'd argue that there's demonstration of success there. The proximity technology that should either machine type get too close to each other, or indeed the dozers get too close to each other, will come in and act as an engineering control to bring it to a safe state. So again, technically possible. Certainly one of the issues we've had is that you can be very sensitive to these technologies, and if not properly, I'll say, configured, you end up with some everything grinding to a halt every few seconds or minutes.
Yes, well, we've got no questions on the Q&A, but Megan has, and sorry, I haven't got Megan's second name, I do apologise. Megan's put a question in through the chat, and I've just picked this up, and it said, and this is Megan's question: Does trust then not come down to the current operators not wanting to have their jobs replaced by machines? How would you suggest that the technology progress with the human barriers that underlie the trust issues? So that's really, yes, human barriers, introduction, people not wanting to be replaced by machines. Do you have any observations on that from your interaction?
I make an observation that everyone's different, and some take that view, some don't. I'd also come back to my main thesis, which is when we conceive these technologies, this is not a consideration that factors into the thinking at all, from the very highest levels, from the very beginning of the problem. And so the problem is not properly articulated. And if it's not properly articulated, the solution won't be the most appropriate or best solution that takes into account all of these issues. And I guess this is my main point, as you know, and I'm guilty of this. We educate many engineers moving into this sector from the University of Queensland, and other universities are doing the same. But nowhere do we bring into our curriculum these considerations. And worse than that, there may not be technologies or the methods, the engineering process, the frameworks that we would like to operate in to achieve this. So I'm of the view, and I'm progressively becoming more of the view, that we really do need to rethink some of the ways in which we go about our education of engineers in order to really change the way in which they act within the workplace. They're not doing anything wrong, but I don't think we're properly framed. We've educated people to properly frame problems in the broader sense. And it becomes critical with these complex technological solutions.
Yes, that's, I guess what I draw out of that, Ross, and we have got some time, is that we now, your hypothesis is we need to educate engineers that are going to be graduating from these institutions to be able to work in a rapidly automating and a world that will be rapidly driven by autonomy, and also be aware of the human factors and the way that these systems work with the ecosystem of people and the production that they're going to have to work in. And,
Roger.
And it is happening at light speed. In terms of the mining industry that you've been covering, and I'm sure Sue's going to be unpacking some of these issues going forward. So look, that's very good. Panelists and attendees, we are actually running about 6 minutes in front of the agenda, which is wonderful. And I'd now like to hand over to Dr. Sue Keay, who is the CEO of the Queensland AI Hub, and has been in this world for a long time. It's part of your background, Sue, as I can read from the biography, and I think we're all looking forward to your views, which is the advances in AI and robotics and their potential applications. So over to you, Sue.
Well, thanks very much, John, and thanks, Ross, for your talk. I'm just going to focus on some of the things that I have seen as having great potential in terms of how AI and robotics might look in the future, and also, if I have time, give a few applications of these technologies that are happening right here now. And maybe some people would be wondering, you know, there is a lot of buzz around artificial intelligence at the moment. And why is that? Because artificial intelligence itself is not a new thing. It's been around since the 1950s. But I think it's really a matter of following the money. We know that worldwide AI spending is, you know, and this number just keeps going up, more than $500 billion. It really is an area where most advanced economies are investing a lot of money, and it's really governments that are leading the way and then encouraging private sector to invest in. And the reason that there is so much interest and investment in artificial intelligence at the moment is because it's time. You know, if you have a look at, this is a car manufacturing plant, the Tesla car manufacturing plant in Fremont, California. It's one of the world's most modern car manufacturing plants. You can see it's got wonderful robots in use there. But in that first shot, all of those robots are still surrounded by cages and are kept separate from people. In many respects, that makes this car manufacturing plant not that different from the original car manufacturing plants that General Motors put in the 1960s, where you had to separate robots from people. And that was because it's at that time, and in some cases today, it's not safe for robots and humans to be operating that closely together. But those times are definitely changing. And the reason that those times are changing is just because of the sheer the huge improvements in computer processing power. Oh, sorry, I've accidentally moved forward. Huge improvements in computer processing power that have happened since we developed the world's first computer back in 1946. And it's not just those improvements in computer processing power, it's the fact that we've been able to miniaturize things, the fact that you now have more computer processing power in your pockets or in your handbags in the form of mobile phones than was ever possible with that 30-ton ENIAC computer back in 1946. All of the components and sensors that go into these into devices are much cheaper than they were in the past. And so the combination of these factors, huge improvements in computer processing power, the ease and affordability of the components to make things like mobile phones and robots, the fact that these things can be miniaturized to such an extent and that they're so light, it makes them very transportable and ubiquitous in our lives. These are some of the factors that are driving the interest in artificial intelligence technologies at the moment. And a couple of key things have really driven this explosion in interest. I'm sorry, my slides have a mind of their own. And one of the most important of these is computer vision. So computer vision powers companies like Facebook and Google. And really, computer vision itself has been around for a long time. It really is just the way that computers or machines interpret visual data, usually from cameras, to work out the next action or to make a decision. But it's not until pretty recently that we've been able to apply computer vision in real time out in the real world. So for example, in days gone past, if you were to put a camera on a robot and ask it to navigate from A to B, then by the time the robot had taken that photo, had processed all of that rich visual information, the scene will have changed and it would not have been safe for that robot to operate. But we're now in a situation where we can place cameras on robots, in fact, very small cameras often, they can be processing information on board in real time that direct the robot with what it can safely do in real time, such as, for example, going up to take a photo of this lion, taking people out of harm's way. The other thing that has had a huge impact on the development of artificial intelligence technologies has been the development of deep learning. So again, my slides have a mind of their own. And this is really just a way of describing how we are getting machines or computers to operate in a way that's more similar to human thinking. So there was a time when if you wanted a robot to do something, you'd have to write lines and lines of codes, if then what statements to describe every particular eventuality that the robot might face and how it was going to cope with that. Whereas now, increasingly, things like robots are learning how to do things in exactly the same way that most of our children learn how to do things, by watching YouTube videos. In this case, we have a robot that is learning about how to grasp a ball by observing how a human is completing that task. And it doesn't have to do that in person. It can be doing it by watching videos of how to do that. And what it means is that instead of having to write those lines and lines of code, that the machines and computers can just learn by observation. And this has been very powerful in terms of expanding the range of applications that artificial intelligence can be applied to. There have been some interesting trends in AI and robotics since COVID first hit. One of these has been the increased appetite for automation or semi-automation that has been caused by COVID. In fact, sadly, or maybe happily, depending on what view you take, there has never been a better time to be an AI or robotics company, because there is such a huge demand for these technologies because of this requirement to try and often access the number of people that are on work sites to reduce their risk of COVID. This has engendered a number of challenges, though. It obviously makes it much harder to do testing when we're also trying to keep people away from work sites. But it has also seen a huge increase in the use of unpiloted aerial vehicle for monitoring sites and for other visual inspection of a range of tasks, so that we don't have to actually have humans on site. There are a couple of, I'm going to talk about 8 main advances that I see really impacting artificial intelligence and robotics. And I'll go through each of these in turn, so I'm not going to list them off. You won't miss any of them. But I think 3D printing is one of the things that really is having a huge impact. We're now at the point where we are being able to print increasingly complex shapes out of an ever expanding range of different materials, which means that we can prototype pretty quickly any type of machine that you might think of developing, and then try it out, see how it works, and rapidly iterate and come up with the best design before ever having to manufacture something. I liken this to the democratization of robotics. So this is an Australian developed robot arm called Dexter, which was developed by Huntington Dynamics, a company based in Toowoomba, which is a 3D printed robotic arm. So it is open source. If you choose to, you could go out and print off this robotic arm yourself. It is very precise, a haptic controlled robotic arm, but the key difference between this and the robot arms that you would have seen in Tesla, well, obviously they're not as large and probably don't do quite the range of things, but is the price point. So if you were the robot arms that you saw in that Tesla car manufacturing plant would typically be upwards of $2 million each, whereas you could make this robotic arm for less than $10,000. Now, what that means is that rather than robotics once only being the sort of thing that you could have on a large production line and where you're a large company yourself, it puts these technologies in the hands of small to medium-sized enterprises, where I'm sure we're going to just see an explosion of different applications of the technology. So as I said, I see this as like the democratization of robotics. It's actually meaning that these technologies are going to be more commonly used by a range of businesses because they can now afford the technology. The other thing that is influencing artificial intelligence and particularly robotics is in material selection. So thanks to artificial intelligence, we now have new materials being thought up or dreamt up by machine learning algorithms, in the thousands every day, far more than a person could possibly get their head around. And what that means is that we also need to use machine learning to select the best material that you might use, for example, to develop a robotic component. So this image is a robotic component or a robotic leg that was being developed at CSIRO's Data 61 when I was the research director there. Or as this title in Wired magazine suggests, it is an example of scientists helping robots evolve and creating weirdness. And certainly that's true. Not only is machine learning now used to help determine the type of material that you might want to build something like a robot leg out of, but then machine learning can be used to actually work out what the design of that component should look like. If you have a look at that strange yellow-green object on the right-hand side of the screen, that is actually a design that an algorithm has come up with for a robot leg that would be best suited to walking through water. And then we can use 3D printing to prototype the robot designed leg. And then our researchers were actually using machine learning to train the robot leg how to walk without any other instructions, just sort of putting it in a test environment and getting it to figure out for itself how it can achieve locomotion. I think the other trend that is really coming to the fore is what I call the roboticization of commodity products, or how everyday items can become robots. Again, this was some research that was happening at CSIRO's Data 61, where this is just a run-of-the-mill trolley. And what you can see is that it has unusual wheels there. And essentially, the trolley has been turned into a robot by virtue of having robot wheels put on it. Now, they came up with some more sophisticated designs for this. So it was more of a tug system rather than having to take wheels on and off to convert the trolley into a robot in its own right. But you can see how this idea could be applied to any number of consumer objects around the house that you might not expect, but that could in the future become robots. And I think that this is something that we will increasingly see. Robots aren't going to look necessarily like robots, but they will be able to function like robots. In some manufacturing facilities, they have such a huge range of trolleys, it's actually not effective for them to purchase automated ground vehicles, which tend to all be the one size. And so it makes sense if they can actually just turn the existing materials that they have into robots. Also can save a lot of money. The other thing that's happening is how sensors or embedded artificial intelligence are just becoming smaller, smarter, and increasingly self-powered. A good example of this is being commercialised by a Queensland company called Tag, which has commercialised some CSIRO technology to develop what they're calling a Fitbit for cows. It can also be applied to other livestock, but you can see it's quite a reasonably sized tag that has a solar panel on it so that it can power itself and it can last for the whole life of the cow. It's amazing. I'm sure it probably happens with our ears too, but if you put an ear on an animal, then you can find out a lot about its health. So you can learn when the animal is eating, when it's sleeping, when it's walking about, when it's ill. And all of that information can then be given to the farmer. And in fact, this technology is processing all of that information on board. It's actually directing it up to a satellite and then directly sending that back down to the farmer. And the reason that that is important is that in days gone past, some of these technologies really didn't gain a lot of traction because it didn't just involve, tagging the cows with an expensive device. It also involved having to put a whole series of nodes around the farm to be able to collect the communication information that was coming off those tags. But we're now getting to the point, thanks to the application of some, clever AI algorithms, that data can be processed on board, sent directly up to satellite, and then communicated back to the farmer. We're also seeing, I think, in the future, a lot more robot teaming. I guess as already has been previewed, in Ross's presentation, Australia was the first country in the world to automate its mine sites. And, we're increasingly seeing different fleets of automated vehicles operating on mine sites. I guess the point that we need to come to is where those automated machines are actually working in conjunction and communicating with one another. And we're already seeing this in transportation, where trucks are experimenting with platooning. You might have a human operator of the first truck or vehicle in a convoy, and the other trucks follow the lead of that operator. Or as Ross was describing, the operator may not even be in the vehicle, they might be operating it remotely. So I think in the future, we're going to see a lot more of this, where one machine will be controlling many. And another example of this, and again, this is back to work that was occurring at CSIRO's Data 61, is the teaming of different types of robots. So this is the part of the team of robots that competed in the DARPA Subterranean Challenge, where the ground-based vehicle, which is manufactured by an Australian company, BIA5, actually took an Emerson drone underground, and the drone was able to launch off the back of the other robot and go and explore the areas that needed to be explored as part of that subterranean challenge. Now, all of this is in communication denied environments. So until recently, this has been a huge challenge still for robots. And the idea is that we need to get to that point where when there is an emergency and perhaps there's been an underground collapse and we don't want to send people in without knowing what the situation is like, that we can actually send robots in and rely on them to be able to provide situational awareness back to the surface so that decisions can be made on how to cope with that challenge. So some of this technology is already in use. For example, Emerson is using the hover map technology that you can see on the bottom of that unmanned, unpiloted aerial vehicle, and currently does a lot of work in the mining industry for stope estimation and other activities where, it's actually just needs to collect the vision information and do some measurements to be able to save the need for having a person go down into that environment to collect that same information. Another local example of how this is being applied has been in the development of the Loyal Wingman. So most people would be familiar. This is the first commercial aircraft being created in Australia for more than 50 years. It is designed and developed here in Australia, and the idea is that the Loyal Wingman will actually work in conjunction with piloted fighter jets and serve the purpose of helping to protect those fighter jets. For those of you perhaps living, in outer space, it should be obvious that our military forces are now facing increased threats from artificial intelligence. And so we need to be able to respond. And this is one way that we can protect our air capability. In fact, it's in the air region where probably most of the AI threats are likely to be faced in the first instance. If you're interested, you might have a look at the Alpha Dogfight challenge, which was another DARPA challenge, which pitted an AI against a human pilot. Sadly, the AI won every single time. And it's just because the speed of reaction time that is able to be produced with artificial intelligence controlling these aircraft is far superior than what we can do as humans. And we need to be able to respond if our armed forces are put into situations where they are facing attacks from artificial intelligence. Another area that I think we will see increasing in the future, although we're not seeing a lot of it just yet, is in the use of exoskeletons. So in Russia, Nornickel has been experimenting with the use of exoskeletons to take away a lot of those manual labour tasks. I haven't looked up the figures, but I'm sure it is still quite distressing to find how many people have their backs injured at work by having to lift heavy materials, and anything technology that we can apply to help reduce that risk is going to be worthwhile. At the moment, some of the main things holding back the use of exoskeletons is that they're still fairly unsophisticated, which means that they themselves can sometimes be very uncomfortable for a human to wear for extended periods of time. But those technology, those limitations of the technology are only going to they will be overcome with time. And then another area which I think is just going to become ubiquitous in the future is the application of digital twins. I found some really interesting use cases of digital twins when we've been out having a look around AI applications in regional Queensland. And one of these is the development of digital twins of forests. So one of our local plantations regularly flies drones with cameras through the forest to create a digital twin. And the reason that they do this is because they will often treat particular trees as their high value wood. So for example, they might treat them, they might actually prune the tree to make sure that the timber is of high quality. But the problem that they have is that 20 years down the track, when they go to actually harvest that tree, it can sometimes be very difficult. The area might be completely different looking, it might be covered in lantana, and then they have trouble identifying where the tree is. But if they have a digital twin, then they know precisely which trees are the high value trees, so they can go in there and do selective logging of the most high value trees. And this is happening in all sorts of different areas. So fisheries, aquaculture, we're now seeing digital twins of whole rivers and sections of the ocean where, using a combination of sensors such as echo sounders, they are actually being able to figure out what type of fish species are in an area, what type of vegetation is in an area, whether fish stocks of a particular type of fish are low, and then importantly for supply chain considerations, actually giving consumers the ability to, by virtue of a simple QR code, figure out exactly where the seafood that they're purchasing was caught at what time before they even make that purchasing decision. So you can have a high degree of confidence about where your seafood is sourced and making sure that it is sourced sustainably. Because the other benefit of these sort of the use of this sort of digital twin is that it can actually give real-time information to our fishing trawlers on what type of fish species they're allowed to capture, and actually instruct them to throw back any species that are at risk of being overfished. So just to give an example of how easy it is nowadays to get a digital twin, this was a quick point cloud that was put together by the CEO of Emerson, Stefan Haber, who was able to take the hover map device. It just becomes a handheld scanning device once you take it off the drone, and he just did a very quick 5-minute walk around. This is the Queensland AI Hub, for those of you who might not have had a chance to come and visit us yet. If you haven't had a chance, please do come and visit us. And as I said, in about 5 minutes, Stefan did a very quick walk around of our space. And based off this point cloud, if we wanted to, we could then convert this fairly easily into a digital twin. So we could have a digital twin of our space. So this sort of technology, again, used to once be the only in the hands of corporations that were able to invest a large amount of money. But we're now getting to the point where this sort of technology is accessible even to small to medium-sized enterprises. And finally, an area which I think is, hugely important in terms of the development of AI and robotics is synthetic data. And this is just to give an idea of, there's just been an explosion in the number of companies that are now we're developing synthetic data sets. And the reason for that is because when we're developing AI algorithms, one of the main bottlenecks is access to data to train machine learning models. By actually creating synthetic data, so data that is generated via a computer program, not necessarily based on any real world phenomena or events, it just means that you can much more quickly train those models up and get a result. There's a number of advantages of this. It can mean that you're preserving people's privacy, so you're not having to rely on, for example, video cameras, in street malls to be able to identify certain phenomena. It means you can generate a large volume of data in a short amount of time. Importantly, what it also means is that you can ensure that there are edge cases in the data, because one of the key problems with using real world data is that if you want to be able to identify a rare event, it might be that you've never captured that on camera to train up your algorithm on. So you can actually make sure that you are putting those edge cases into your training data sets by using synthetic data. So you can imagine, for example, in the case of autonomous trains, there is monitoring of those railway tracks. It might be that people never go near those railway tracks for many months, but the incident where you want the train to be aware is that one case where someone has come near the train track, so that then the system can intervene and stop the train. And so again, I guess this is just to give you a bit of a background of why there is this huge proliferation in the number of synthetic data companies. One of these, Yuva AI, is a local Queensland-based company, but there are going to be far more of these in the future and will enable us to do far more things, and hopefully for us to be able to rely on these AI systems much more, because they are going to be able to recognise rare and unusual events. Now, I think I have enough time to just quickly show off some applications of these sorts of technologies. And I really had to cut back my slide deck. I could keep talking about this most of the day. These are just a couple of my favorites to show you the range of different areas where these technologies are having an impact. So you might recognise this red platform from one of the previous slides. This is BIA5's Ozbot ground vehicle. I love this. This is one of my favourite companies. It was started by 2 Queensland police officers who worked in the tactical response unit, who were after a robot to help them in their work, went through some robot catalogs, couldn't find anything they liked, so decided to start their own robotics company. And this is one of the results. So not only have they looked at how you can use these robots for tactical response, they are now looking at how they can be applied in other areas. In this case, this is how the robot might be applied for firefighting, which is clearly an area where if we could be able to send in robots rather than putting humans at risk, it would be a good thing. Another application area is for the environment. A lot of people don't think of how robots and artificial intelligence can be used to help preserve the environment, but this picture is of QUT's RangerBot, which is a robot that not only monitors the Great Barrier Reef and collects data about the reef health, it can actually also take action and be used to help reduce the number of crown-of-thorns starfish on the reef. They've undergone a number of iterations, but I think it's a good example of how these technologies can be helped to solve quite large environmental challenges. These technologies are increasingly being used to help us with monitoring all of the infrastructure. As everyone would be aware, Australia is covered in thousands of kilometres of roads, rail lines, pipelines, power lines, railway bridges that all need to be inspected for safety and efficacy. And it really is a case of us not having enough people to be able to inspect all of this infrastructure. So people are increasingly using unpiloted aerial vehicles to be able to collect this information. Another interesting application of AI is by a local company called Movis that has developed what they call a Fitbit for machines. So it's that little orange round tag on the side of that machine. And essentially it is using artificial intelligence to have a look at the vibration monitoring data that the device is collecting, and then using that information for preventative maintenance purposes. So it can very accurately predict when a machine is likely to fail. And this has important consequences on production lines. So it means that, for example, rather than waiting for a machine to fail and then having to find a replacement and potentially having a production line down for hours, if not days, it will give enough information to predict when that machine is likely to fail so that those preventative steps can be taken and potentially very little downtime in production be experienced. There are a huge number of applications in healthcare. Again, this is a locally developed one based on University of Queensland research. This is a mobile phone app called ResApp. Essentially, what this device does is you can cough into your phone and it will diagnose your respiratory illness. Now, it is only licensed to be a diagnostic tool, which means you would do this in conjunction with advice from a general practitioner. And the general practitioner would get you to use the device and then would actually interpret the diagnosis that the machine gives and give you a treatment plan. But you can see how in time of COVID, this is very useful. So you can have someone out in a remote area, they just need to download the app, cough into the phone, and their respiratory illness can be diagnosed. Another local example is Steffi, which is an electronic stethoscope that can record and also diagnose whether there are any problems with your breathing or heartbeat. And again, in the times of COVID, when we're trying to have people separate from other people and not put our medical staff at risk, this is a great application of artificial intelligence. Another area where we're seeing these being applied is in service delivery. So there is currently a trial at Logan City by Google's Wing service of unpiloted aerial vehicles delivering packages. This does look like it's something that is very likely to be happening in Australia in the near future. Just to give you another out there example, this is a company called Popgun AI. I think they've just changed their name to Splash because they developed a hugely popular application and game called Splash, mainly used overseas rather than in Australia, but they have more than 8 million users. And it's a way that you can use artificial intelligence to generate music. And for those of you who don't know, Australia actually won the Eurovision AI Song Contest last year, and this is the winning band. They're called Uncanny Valley, and their song Beautiful the World, I recommend you look up, but it is generated by human composers using artificial intelligence, very cleverly done. And I think I like to finish off with this example because it just shows the huge range of applications that we are now seeing for AI and robotics, and the impact that these are going to have on every sector of the Australian economy and indeed of our lives. And I would hope that people aren't frightened of these applications. In the case of Uncanny Valley, the composers actually see AI simply as a tool that helps them to do some cool stuff that they weren't able to do in the past. And that's the way I view a lot of these technologies as well. Ross has gone over some of the implications of, you know, what does it take to make these systems trusted? But I think that one of the key things that needs to happen is that we actually need to see more of these AI tools and robots out in people's hands so that people can experiment with them and reduce the fear factor of how the technology is being applied. Anyway, I'm going to leave it there, John. Hopefully that's given a quick overview of where I think things are likely to be heading in the future. Thank you.
So thank you very much. And you took us through a really expansive world. I congratulate you for getting the word weirdness into a presentation. That's a first for me. So I'd like to remind the attendees that the Q&A is now open, and we're waiting for Q&As to come through. I just do have one that's kind of topical. You took us through many areas: the power, computer vision, deep learning, how COVID is accelerating. When we got to the printed, the open source printed robotics and the micro printing of anything, of devices, what came to my mind was advanced manufacturing. In that, you know, we are a small company, we don't have we've got no car industry anymore. Are you seeing the opening up? Because you'll have a view on this. Would you like to give us a view on the opening up of the advanced manufacturing opportunities you can see coming as the robotics, as AI, as these smaller, higher value opportunities arise? Do you have any views on Australia and where we can go with that?
Yeah, well, yeah, there's a few complicating factors there. I think one of them is that, for example, you know, if we really wanted to be able to have sovereign, you know, protect our sovereign supply chains, then, you know, one issue that happened during COVID was actually supply of many of the plastics used in 3D printing. So I guess that there are a number of levels that we'd probably have to look at to be able to make sure that we could do everything in Australia. But I think that where Australia has its strengths in manufacturing are increasingly around niche manufacturing, because it's the only area where, you know, we have an advantage because we're doing something potentially innovative. It might be we never do sort of high volume, low cost production. It's always going to be low volume, high cost or potentially high quality production, and these are just simply tools that are going to make that a lot easier to do in the future, that will help us prototype things, iterate on the best design quickly and make us more efficient at doing that, and just keep us competitive. And what we're seeing in countries like the US is increasingly the onshoring of work back to their country, and we're already seeing signs of that in Australia. And I think the other really heartening sign is that in the US, what they're now seeing is that any increase in automation in manufacturing is also being matched by an increase in investment in training of staff. So I would hope, we don't have the data on that in Australia as far as I'm aware, but I would hope that we will see the same trends. So some of the questions that were coming up in Ross's session about, well, okay, so maybe people aren't taking on the technology because they don't like it and they don't really want their jobs replaced. In manufacturing, and I would hope we'd be able to see this in mining too, it's actually opening up more opportunities. It's making businesses more profitable. And as those businesses become more profitable and they're potentially adding on new product lines, it means that they have the capacity to take on a more small workforce, and that workforce, though, probably needs to have training in different areas. And that challenge of how we reskill people is going to be really important in the future. But I just find it really encouraging that the signs that we're seeing in a country like the US of that increased investment in training of staff is going to be critical. And I think that's true for, no matter where these new technologies are being applied, it has to be done in conjunction with, ways that are making people feel more comfortable in using those tools.
So one here, we've got the AI Hub here in Queensland, and is part of the AI Hub direction and other support from the government is to raise the awareness of the requirement for training? And are we getting those links back into universities in the undergraduates and also into the skills colleges?
Yeah, I think that TAFE is really leading the way in that respect. I think that people are increasingly becoming aware that workforce planning is important. I don't think that we can get that message out there enough, though. And in fact, I'd like that tied in with corporate social responsibility. I mean, I think it's really important that when people are thinking of where that they should be investing their funds, that they should look at how well corporations are undertaking this process of workforce planning, because it affects everyone. If we, and I mean everyone. So if we're not preparing all of our workforce for these new technologies, then we're not doing the right thing. But certainly TAFE has a number of micro-credentials and courses that are really setting people up. What we're seeing are some really good examples, companies like Rio Tinto working with TAFE to develop courses for their new entry-level jobs that I think the new entry-level job for Rio Tinto is a field technician. So making sure that people have access to courses that would enable them to be skilled for that job is increasingly important. But at the moment, we're mainly seeing that from the large corporates, and we need to see that starting to come down to the small to medium-sized enterprises, because in Queensland, 90% of Queenslanders are employed by companies that have 20 people or less, and all of those companies need to be going on this journey of how they can transition their workforce to use these new technologies.
Now, it is always said that you leave the tricky questions till last. So I've got a tricky question for you, Sue. It's from CN, and he says, great talk, and I think we all thoroughly agree with that. He asks, what do you think are the areas that AI should not be allowed to develop in?
I don't know that you can put a ring fence around it. It's interesting you raise that, because I think that people's perceptions of how AI should be used and reality, I think, have not necessarily been tested. So what we know is that when people are surveyed about applications of things like robots, one thing that people are pretty clear on is that they do not want robots used in childcare. And there are a couple of other things that really people just go, no, never, not going to happen, don't want that. And yet, I think that that's probably only because we've not been exposed to some of the potential opportunities. So one of the social robots that we worked on, we never got the chance to test this idea, but robots are endlessly patient, which can be very useful in dealing with children. And so you can imagine taking a bit of burden off teachers by giving them teacher aid robots that remind kids that they need to go and wear a hat when they go outside, rather than the teacher having to stand there and for every child that goes past going, no hat, no play, no hat, no play, no hat, no play. You just get the robot to do that. I don't know. I think that until we actually see more robots and AI out and about in the community, we still have to test that. But my personal view is that I can't think of anywhere immediately. That's not because I think it's a good idea to use AI in all circumstances. It's more that I just don't think, how can you actually prevent it? It's like saying, for example, we often hear, that there is a concern that AI might equal job loss. Personally, I don't agree with that. I think AI will lead to endless job creation, but it will lead to some jobs being displaced. But it's not as if Australia can just say, you know what, we've decided we don't want artificial intelligence here. Yeah. We use it every day without even thinking about it. And you just the genie's out of the box or out of the bottle.
Well, one reflection, it's your present. I'll give it a reflection for the audience and the panelists. I visited Japan on a private visit recently, and was exposed to the use of robotics and machine learning AI in the aged care sector. It's a rapidly aging society, as is as we all will become. And one Japanese person said to me that I was amazed by it. And he said, the use of this technology is limited by our imagination. So that's just a reflection. It's a personal reflection. So we are at the we're closing out. I'm going to open up for any general questions before we close out the whole session. Is there anything else coming through? Are there any questions that we'd want to ask for Ross and Sue together? Well, the answer is I don't have any questions coming through. So on behalf of ATSE and on behalf of all the attendees, I'd really like to thank you, Sue, and you, Ross, for putting these presentation packs together. These are endlessly fascinating subjects, and they are the future. The future is here today, and I think what we've stressed with your views, Ross, on the education dynamic, and Sue, you took us through a whole wide range of robotics and AI in all aspects of daily life, and one can think about how that's going to accelerate away. I think you've helped us a lot to think our way through this. I'd like to thank you very much, and absent any questions, I think now is the time to bring this excellent session to a close. Thank you very much.